Namaste students, welcome back to Rama Teacher Suite. Today we're going to do the next video on chemical bonding and molecular structure. Okay, so we have already done I think we started with MOT and we studied the molecular orbital diagram for the H2 molecule. So we are going to continue with that in today's class. Most probably we'll finish this chapter. Okay, let's continue. So, um, where were we? Yeah. So in molecular orbital theory, there was a couple of things that we need to understand first. Okay, that was number one. You had the bonding molecular orbital, and then you have something known as the anti-bonding molecular orbital. So what is the difference between a bonding molecular orbital and an anti-bonding molecular orbital? A bonding molecular orbital is formed when the wave function are in perfect synchronicity with each other. That is, when one wave function overlaps with the other, you get what? A constructive wave. And that constructive wave leads to what? Leads to a bonding molecular orbital. So for example, if you have a wave function A and another wave function B and they both are in sync with each other like this, if they're both in sync with each other, then we can say that they are part of the bonding molecular orbital. And in the case of the anti-bonding molecular orbital, what do we get? We get that they are 180 degrees out of phase with each other. So therefore the resultant wave is actually smaller. It has a smaller amplitude as compared to the actual two waves. Okay, and what happens? What is the main difference between a bonding molecular orbital and an anti-bonding molecular orbital? In a bonding molecular orbital, the electrons are present between the two nuclear centers. Okay, because they are present between the two nuclear centers, what ends up happening? The repulsion, okay, the repulsion between the two nuclei is actually reduced due to the presence of negatively charged electron cloud between them. Whereas in the case of anti-bonding molecular orbital, there are no electrons present between the two nuclei. Therefore, the repulsion is much more. Due to which what happens? Due to which the anti-bonding molecular orbital has more repulsion and therefore it becomes less stable. The bonding molecular orbital is more stable, whereas the anti-bonding molecular orbital is less stable. Now, stability comes at a price. Stability basically is directly related to the energy. So, a bonding molecular orbital will be at a lower energy level than either of the atomic orbitals that are taking part in actually forming the orbital. Okay, whereas in the case of the anti-bonding molecular orbital, the overall energy level is higher due to the repulsion that exists between the two nuclei. So you are at a higher energy level. But one thing that you have to understand is that you are not creating new energy. New energy is not being created when you are forming a bonding or an anti-bonding molecular orbital, because the energies that both the orbitals, the atomic orbitals, had in the beginning before they actually combined themselves to form the bonding and the anti-bonding molecular orbital will be the same as the energy levels, the sum of the energy levels of the BOT and the AOT. BOT is the bonding molecular orbital, sorry, BMT and AMT. Okay, so the bonding molecular orbital and the anti-bonding molecular orbital energy summed up together will be equal to the sum of the individual atomic orbitals of both the atoms. I hope till here you have understood. Drupad, is it clear? Yes or no? Yeah, yeah, perfect. Okay. Now, when it comes to the types of molecular orbitals, there are three or more types of orbitals. So you have the sigma, the pi, and the delta. In your case, you're only going to be interested in the sigma and the pi bonding molecular orbitals. Okay. So the bonding molecular orbitals are represented by sigma, pi, and delta, whereas the anti-bonding molecular orbitals have a small star on top, that is sigma star, pi star, and delta star. So this is where is the star? Let's see. Mm, where was it? Yeah, exactly. See, the bonding molecular orbitals are represented by sigma, pi, and delta, whereas the antibonding molecular orbitals are represented by sigma star, pi star, and delta star. So, till here, no problem. Okay, then we actually started understanding how the combination actually works by studying a few diatomic molecules. Now, diatomic molecules are those molecules that have at least two atoms that have two atoms in that molecule. Okay, so in the case of H2, okay, what is happening in the case of H2? Two hydrogen atoms with their 1 electrons in their outermost shell. They only have one shell. With their 1 electrons, they are coming together and actually forming a bond. Okay. Now, in this case, what is going to happen? The linear combination of the 1s orbital centered on two nuclei gives two molecular orbitals. Okay. Two atomic orbitals, when they come together, they make two molecular orbitals. Okay, it's the same as the case of hybridization. Two orbitals gives you two hybrid orbitals. Three orbitals gives you three hybrid orbitals. Similarly, two atomic orbitals come together to produce two molecular orbitals. Okay, so the atomic orbital 1s and the atomic orbital of 1s of two hydrogen atoms are coming together to form sigma 1s and sigma star 1s. That is one bonding molecular orbital and the other anti-bonding molecular orbital. Okay, till here the story is pitch perfect clear, right? Good. So now this is how the bonding and the anti-bonding molecular orbital actually looks like. Okay, the linear combination of 1s orbital centered on two nuclei gives two molecular orbitals that are symmetrical around the bond axis. They are perfectly symmetrical. Such molecular orbitals are of the type sigma type, and they are designated as sigma 1s and sigma star 1s. Okay, next. Similarly, the 2s atomic orbitals, so 1s and 1s combine to form sigma 1s and sigma star 1s. 2s and 2s are going to combine to form sigma 2s and sigma star 2s. So, sigma 2s and sigma star 2s will be used to represent the helium atom. Now, how do you form this? So, at the beginning, you write here, you draw a line like this. So, what about the next one? The 2pz and the 2pz. 2pz and 2pz would form what? Sigma 2pz and sigma star 2pz. Clear? Next, your 1s and 1s. 1s and 1s will form the sigma only. So, S will always form sigma, P will form sigma as well as pi. Remember that. Okay. S will only form sigma, whereas P will form sigma as well as pi molecular orbitals. Now, this 2py and the 2py, again the same story. You will get pi 2py and pi star 2py. Clear? Any doubts till now, Drupad? Okay, let's move on. Energy level diagram for molecular orbitals. Okay, you have studied that 1s atomic orbital forms two molecular orbitals designated as 1s sigma 1s and sigma star 1s. Similarly, the 2s and the 2p atomic orbitals, 8 atomic orbitals on two atoms. Okay, 8, yeah, overall 8, because see, the 2s has one atomic orbital and the 2p has three atomic orbitals. And if this is present in one atom, therefore 8 atomic orbitals will be present in two atoms. Okay, so 8 atomic orbitals are combining. Then if 8 atomic orbitals are combining, then you will get how many molecular orbitals? You will get 8 molecular orbitals too. Okay, so the bonding molecular orbitals will become sigma 2s, sigma 2pz, and then you will have the pi molecular orbitals, pi 2px and pi 2py. Similarly, you will have the anti-bonding molecular orbitals. Okay, so 8 atomic orbitals came together to combine and form 8 molecular orbitals. The energy level of these orbitals have been determined experimentally from the spectroscopic data of homonuclear diatomic molecules of the second row elements. When I say homonuclear diatomic molecules, what I'm trying to say is that you have the H2, sorry, not H, um, N2, O2, your basically F2, all of these. Okay, these are all diatomic molecules of the second period. Okay, now in the case of O2 and F2, the increasing order of energies of various molecular orbitals follows the order sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, sigma 2pz. Then you have the pi 2px and the pi 2py. Now, the pi 2px and the pi 2py are at the same energy level. Okay, so you have to be very careful. Similarly, you have the pi star 2px and the pi star 2py and the sigma star 2pz. Okay, this is only for oxygen and fluorine because of their increased electronegativities. Whereas in the case of others like lithium 2, beryllium 2, boron 2, carbon 2, nitrogen 2, so these are also diatomic molecules. However, the above sequence of energy levels is not true in the case of many molecular orbitals. So, what does their off-bow arrangement look like? It looks like, again, sigma 1s, sigma star 1s is the same. Sigma 2s, sigma star 2s is the same. But instead of the Z, the sigma 2pz being lower than the pi value, it shifts. So you get pi 2px, pi 2py in the beginning, and then sigma 2pz. Then you have the pi star 2px, pi star 2py, and then you have the sigma 2pz. So I'll just give you a rough explanation of how you are going to make this. Okay, so you have one is oxygen, and then the next one I'm going to take nitrogen. So Drupad, how many electrons are present in the O2 molecule? One oxygen atom has how many electrons in the outermost shell? I'm only interested in the outermost shell. Six. Yeah. Okay, six. So this is how the arrangement is going to go. Sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. Then you have the sigma 2pz. Then you will have pi 2px, pi 2py. Then you will have pi star 2px, pi star 2py, and then sigma star 2pz. Okay, now this is what oneness. This results in the formation of two molecular orbitals, 2s and 2s. This again results in the formation of two molecular orbitals. Then you have the 2p and the 2p here. Now, because 2p and 2p have how many atomic orbitals? They have three atomic orbitals each. So, in all, they will form six molecular orbitals. Okay, this is how the orbital formation actually takes place. I will draw much detailed pictures in the future, but I'm just going to trying to explain this to you. Okay, similarly, in the case of N2, what do you get? The initial arrangement till here is going to remain the same. Okay, look at this. Sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. Then you have the okay yeah, pi 2px, pi 2py, sigma 2pz, pi star 2px, pi star 2py, sigma 2pz. Okay, so only this arrangement is different. Okay, you have sigma pi pi sigma for oxygen and fluorine, then you have pi sigma in the case of the rest of the molecules of the second period. Understood? So only the 2p orbitals is going to change here. Okay, whereas the 1s and the 2s are exactly the same, only these two are different. So in the case of oxygen and fluorine, one is sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, pi sigma 2pz, pi 2px, pi 2py, pi star 2px, pi star 2py, and sigma star 2pz. Okay, sigma pi pi sigma. Similarly, in the case of nitrogen, you will have sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, then pi 2px, pi 2py, sigma 2pz, pi star 2px, pi star 2py, sigma star 2pz. Understood how the electrons are arranged? Okay, so in the case of oxygen and nitrogen, okay, these are two different, they're going to have two different electronic arrangements. Okay, in the case of oxygen, you're going to have sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. This is going to be the same for almost all the molecules that you're going to study. Okay, the only difference that is going to be seen is that in the case of oxygen, for the 2p molecular orbitals, you have sigma pi pi sigma. Okay, whereas in the case of nitrogen, you are going to have pi sigma pi sigma. Okay, sigma pi pi sigma, and then you have pi sigma pi sigma. Okay, only these two. Do you see? These two's arrangement gets flipped. Okay, Dhruvat, is it okay? Okay, okay. Now, important characteristic features of this order. Why is it so important? Is that the energies of sigma 2pz molecular orbital is higher than that of pi 2px and pi 2py molecular orbital. Okay, then sigma is greater, okay, than pi. Okay, next. So this is how you are supposed to draw the arrangement. Okay, you will draw from the beginning. So this box will indicate your sigma, sorry, 1s orbital, the 2s and the 2s orbital. Then you have the 2p atomic orbital with the 2p atomic subshell, which contains three orbitals. Okay, 2px, 2py, and 2pz. Okay, this is the increasing order of energy. Okay, this we have to draw, and this is the whole arrangement. So here sigma pi pi sigma, this is for what? Oxygen and fluorine. Okay, but in the case of the others, what happens? You have pi sigma pi sigma. Okay, for lithium, beryllium, boron, carbon, nitrogen, all these diatomic molecules will have these two orbitals flipped from that of oxygen and fluorine. Okay, so again I'm saying sigma pi pi sigma for oxygen and fluorine, pi sigma for the rest of the diatomic molecules of the second period. Okay, let's move on. Now, the electronic configuration and molecular behavior. How does the molecule behave when you have given it such a structure? Let's see. Okay, the distribution of electrons in various molecular orbitals is called the electronic configuration of the molecule. Now, Drupat, do you remember when we actually started studying the atomic orbitals, we started giving an electronic configuration for various elements? Like in the case of hydrogen, the electronic configuration was 1s1. In the case of helium, it was 1s2. In the case of lithium, it was 1s2, 2s1, or simply helium 2s1. And in the case of oxygen, what was it? It was 1s2, 2s2, 2p4, or simply helium 2s2 2p4. Do you remember this electronic configuration that we used to write for the atoms? Similarly, we can draw, you can write the electronic configuration of molecules. Okay, electronic configuration of molecules depend on the way the electrons are arranged in the molecular orbitals. Okay, so let's actually slowly and slowly understand how we write the molecular orbitals. Now, the distribution of electrons on various molecular orbitals is called the electronic configuration of a molecule. Now, the electronic configuration gives the following information which is given below. First things first, the stability. If the number of electrons occupying the bonding orbitals are represented by Nb, and the number of electrons occupying the anti-bonding molecular orbitals by Na, then what happens? Then the molecule is stable if the number of electrons present in the bonding molecular orbital is greater than the number of electrons present in the anti-bonding molecular orbital. So think about it this way. Okay, the bonding molecular orbitals, the bonding molecular electrons, okay, they are responsible for keeping the molecule together. Okay, so they are reducing the internuclear forces of repulsion between the two nuclei of the two atoms. So they are responsible for keeping the peace, whereas the antibonding molecular orbitals have electrons which do not actually do much to reduce the repulsion. They actually don't do anything. Okay, they actually make the problem even more worse. So it is like the bonding molecular orbital electrons are the friends of the molecules, and the anti-bonding molecular electrons are the enemies, or basically the protesters of the bonding molecule. Now, if you have more friends than enemies, you will be stable. If you have more enemies than your friends, or equal number of enemies and your friends, then you are at risk, right? Your position is at risk. So more friends, less enemies always results in stability. More number of electrons in the bonding molecular orbital compared to the anti-bonding molecular orbital, the molecule remains stable. But if you flip it, if you make it equal, then what happens? Then the molecule will become unstable. Okay, we are going to understand more about this in the coming lectures. Okay, so if the molecule is unstable if the number of bonding molecular orbitals is less than the number of electrons present in the anti-bonding molecular orbitals. Even if they are equal, even if you have the same number of friends as enemies, then also you're not stable, because there is always a chance of splitting up. The molecule may split up. Okay, so the bond order, as already defined, it is one half of the difference between the number of electrons present in the bonding and the anti-bonding molecular orbital. Okay, so basically the it is 1 by 2 of Nb minus Na. If Nb minus Na is greater, then the bond order will become positive. Okay, if it is positive, then what happens? The molecule is stable. But if Nb is less than Na, or if Nb is equal to Na, then the bond order becomes 0 or negative. When such a type of molecule is formed, what happens? It becomes unstable. So the bond order also helps in determining whether the molecule is stable or not. A positive bond order will always result in what? A stable molecule. A zero or a negative bond order will result in an unstable molecule. Okay, the nature of the bond. If the bond order is 1, 2, and 3, it shows the presence of a single, double, or a triple bond respectively. Okay, so if bond order is 1, that means it is a single bond. If bond order is 2, for example, in the case of oxygen, there is a double bond that is present. Therefore, the bond order of oxygen molecule will become 2. The bond order of nitrogen molecule, because of the presence of a triple bond between the two nuclei, the bond order will become 3. Okay, next, the bond length. It is a measure with the help of bond order. Now, if the bond order is higher, then what happens? automatically the bond length reduces. We know that the single bond is bigger compared to that of a double bond, and the double bond is bigger compared to that of a triple bond. So triple bond has the shortest bond length. The higher the number, higher the positive number of the bond order, the lower is your bond length. Am I clear? Drupad, am I clear? Okay. Then the magnetic nature. If all the molecular orbitals in a molecule are doubly occupied, that is, not even a single molecular orbital has a unpaired electron. If they don't have an unpaired electron, then automatically what happens? The molecule becomes stable. Sorry, the molecule becomes diamagnetic. Okay, but if there are unpaired electrons present in any of the molecular orbitals, then what happens? It becomes paramagnetic. And as we have already discussed, a paramagnetic and a diamagnetic material, how does it differ from each other? A paramagnetic material will allow the flow of magnetic field through itself, whereas a diamagnetic molecular orbital would try to repel it. It won't allow the flow of the magnetic field through its body. Okay, that's how the that's how the paramagnetic and diamagnetic materials differ from each other. Okay, now I'm going to show you a video very soon showing that oxygen molecule is a magnetic molecule. That is, if you place an oxygen molecule in the presence of a magnetic field, it will actually get stuck to the magnetic poles, just as if the if you see if you place a magnet in an iron filings, okay, what happens? The iron filings get stuck to the magnet, right? Similarly, I'm going to show you how an oxygen molecule actually gets stuck in between the two magnets, the two poles of a magnet. I'll show you that video. Okay, now bonding molecules in homonuclear diatomic molecules. Now, homonuclear means what? Homo means similar. Okay, so similar. If you have two same atoms coming together to form a diatomic molecule, for like in the case of Li2, Br2, then you have the, for example, N2O2. Okay, so these all molecules are called what? They are called diatomic homonuclear, not diatomic, yeah, diatomic homonuclear molecules. Okay, here the term homonuclear means that there is only one type of nucleus, that is, one element is present, and a diatomic means that the molecule is composed of two atoms. Okay, examples of such molecules are given below. First one is the hydrogen molecule. Okay, now in the case of hydrogen molecule, hydrogen atom, two hydrogen atoms are coming together to form the hydrogen molecule. They are bringing with them how many? They are bringing with them one electron each to get us two electrons. Now, there is one electron that is present in one of the atomic orbitals of each hydrogen atom. So, two atomic orbitals come together to form two molecular orbitals, the sigma 1s2 and the sigma star 1s2. Now, both the electrons are going to get filled in one of the molecular orbital first, and we know the rule. We know that it follows the Aufbau principle. What does it mean? It means that every single molecular orbital at a lower energy level will get filled up first. So, since the sigma 1s2 is at a lower energy level compared to that of sigma star 1s2, we get to see that the one sigma 1s2 is filled first, and the sigma star 1s2 does not have anything. So both the electrons actually went inside the 1s2 molecule. Now, if you look at the following characteristics, what are the characteristics that we have learned here? We have learned about the stability of the molecule. Now, is the hydrogen molecule stable? The big question. We know that if Nb, number of electrons in the bonding molecular orbital, is greater than the number of electrons in the anti-bonding molecular orbital, then the molecule is stable. So, in the bonding molecular orbital of hydrogen, how many electrons are present? There are 2 electrons present in the bonding molecular orbital, and there are 0 electrons present in the anti-bonding molecular orbital. So you get Nb minus Na is equal to 2 minus 0 is equal to 2. And that is a good thing for us, right? Therefore, we can say that the H2 molecule is stable. Understood, Drupad? Okay, next we learned about the bond order. What is the formula for bond order? 1 upon 2 Nb minus Na. So 1 upon 2 Nb minus Na will give us what? 1 upon 2, 2 minus 0 is equal to 2 upon 2 is equal to 1. So the bond order is equal to 1. So having a bond order means that again the molecule is stable. If the bond order was 0, then the molecule would have become unstable. Okay. Now the bond order being 1 indicates what? There is one single bond present between the two atoms of hydrogen. Okay. So there is one single bond present between the two atoms of hydrogen. Okay. 1 indicates a single bond. Clear? Next. The bond order is 1. The electronic configuration is what? Sigma 1s2. The sigma 1s2 is the electronic configuration. The bond order is equal to 1 means that two hydrogen atoms are bonded together by a single covalent bond. The bond dissociation enthalpy of a hydrogen molecule has been found to be 438 kilojoules per mole, and the bond length is equal to 74 picometers. Since there is no unpaired electrons present in the hydrogen molecule, this is diamagnetic, right? There are two molecular orbitals, and none of the molecular orbitals contains an unpaired electron. All the electrons are paired. Okay, so therefore what happens? It becomes a diatomic molecule automatically. So it does not allow the magnetic field lines to actually pass through it. Okay, now let us take the example of helium. Now, in the case of helium, what is happening? You have two atomic orbitals from two helium atoms. They are bringing with them what? 4 electrons, 2 in each atomic orbital. So, with these 4 electrons, we can fill both the bonding molecular orbital as well as the anti-bonding molecular orbital. Now, when we fill both of them, what do we see? We see that Nb minus Na is now becoming 0. Now we know that if Nb minus Na is equal to 0, then what happens? The molecule will become unstable. So this is one of the major reasons why the helium molecule does not exist, right? Helium is a noble gas. It can stay on its own. It does not have it does not have a requirement to basically bond with anybody. Okay, so the helium molecule does not exist. This is the reason why. Okay, now the helium molecule does not exist. The bond order becomes what? 1 by 2 into 0 is again 0. So the bond, how many, what was it? What was the name? Nature of the bond. The nature of the bond does not exist in the case of helium. The nature of the bond does not exist. There is no bond length also. Similarly, what happens? The number of electrons present in both the molecular orbitals is full. Therefore, you will get a diatomic molecule. If this molecule ever existed, you would get a diatomic molecule. What would the electronic configuration of such a hypothetical molecule be? Sigma 1s2, sigma star 1s2. Am I clear? Sorry. Okay. So bond order 0 means that helium molecule is unstable and does not exist. Similarly, it can be shown that Be2 molecule, sigma 1s2, sigma star 1s2, sigma 2s2 or sigma star 2s2 does not exist. Okay, because again what is happening? Just like in the case of helium, Be2 will not exist because the number of electrons present in the bonding molecular orbital and the number of electrons present in the anti-bonding molecular orbital are the same. So Nb minus Na becomes 0. The bond order becomes 0. So the molecule will not exist in nature. Am I clear? So if they ask you why does He2 not exist or Be2 not exist, this is the reason that you have to provide. Am I clear? Very good. Now, lithium 2. Lithium 2 is also a very interesting molecule. Now, can you tell me the atomic number of lithium? The atomic number 3. Now, the electronic configuration 1s2, 2s1. Am I right? So, let's actually draw the molecular orbitals of lithium together. So, we have 1s from one lithium, another 1s from other lithium. Oh, what happened? Okay, then you have the 2s from one lithium, another 2s from another lithium. So this is 1s, 1s. This is lithium A, this is lithium B. Okay, now oneness and oneness are bringing with them how many? 2 electrons each. So all in all, 4 electrons. So this will form two different types of molecular orbitals because two atomic orbitals are present. Okay, two atomic orbitals will give us two molecular orbitals. So what will this become? This will become sigma oneness, sigma star oneness. So these two electrons will get filled up here and these two electrons will get filled up here. Now, in the case of 2s, what is happening? 2s, lithium only has one electron. In here also, lithium only has one electron. So, these two atomic orbitals again are going to produce two molecular orbitals. Okay, so this is sigma 2s and this is sigma star 2s. So, these two electrons, they won't get filled individually because the sigma 2s is at a lower energy level as compared to sigma star 2s. Both the electrons will go downwards, both the electrons. Okay, now the energy level will go like this. So what is the electronic configuration of lithium going to be? Li2. Li2's electronic configuration will be sigma 1s2 sigma star 1s2 sigma 2s2 sigma star 2s2. Okay, no, sorry. There is not going to be sigma star 2s2 till here only. So this is going to be the electronic configuration of lithium 2. Now, as we can clearly see, the number of electrons that are present in the bonding molecular orbital is greater than the number of electrons present in the antibonding molecular orbital by 2. So Nb is equal to 1, 2, 3, 4. 4 electrons. Na is equal to just 2 electrons. So bond order becomes equal to Nb minus Na is equal to 4 minus 2 is equal to 2. The bond order is 2. Okay, therefore it is stable. What is the nature of the bond going to be, Drupad? No. That is magnetic property. Nature of the bond will be double bond. Okay, and then the magnetic property. It will be dimagnetic. Okay, it will become dimagnetic. I would really like you to remember the bond enthalpy and the bond length of hydrogen. The rest you don't have to remember. Okay, like the bond length of hydrogen is 74 picometers. The bond enthalpy is 438 kilojoules per mole. But for the rest, you don't have to remember them. Okay, this is how the molecule is going to look like. They have given us the electronic configuration. The bond order is, oh wait, I'm so sorry. The bond order is not 2. I forgot to write the 1 by 2. Okay, Drupad, remind me these things. So this becomes 1. The bond order is equal to 1. So it is stable, but the nature of the bond is going to be a single bond. Okay, it is going to become a single bond. It will be diamagnetic. Okay, I forgot to write that. I'm so sorry. Now, this is 1. So the bond order is equal to how much? 1 means Li2 molecule is stable and contains no unpaired electrons. Hence, it is diamagnetic in nature. It has a single bond between them. Now, next, carbon 2. In the case of carbon 2, what happens? The electronic configuration of carbon is 1s2, 2s2, 2p2. So it has 6 electrons. So there are 12 electrons in carbon 2. Now let's actually draw this. Okay. Now if you want to draw a rough sketch, what will you do? You will write 1s, sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, sigma 2pz. Then you have no. In the case of carbon, you have what? The electronic configuration goes as what? Sigma, 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 and then you have pi, sigma, pi, sigma. Okay? In the case of oxygen and nitrogen, it is sigma, pi, pi, sigma. Otherwise, in the case of carbon, it is pi 2px. Sorry, pi 2px, pi 2py. Then you have sigma 2pz. Then you have pi star 2px, pi star 2py. Then you have again sigma star 2pz. Okay, so carbon has oneness, oneness. It has both electrons in its oneness. So this will get filled up. This is what sigma star oneness, sigma oneness. This is what sigma 2s, sigma star 2s. Okay. So these two molecular orbitals are filled up. Then you have the 2s. This will become sigma. This also has 2 electrons. This also has 2 electrons. So these orbitals will also get filled. Then you have how many electrons here? 2px, 2py, 2pz. Similarly, you have 2px, 2py, 2pz. There is one electron here, one electron here, one electron here, and one electron here. So the pi 2px and the pi 2py both will get filled up. Okay, both of them will get filled up. The sigma 2pz won't get filled up because there are not many electrons left. So what does the electronic configuration become? Sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px and pi 2py. Okay, pi 2p x2, pi 2p y2. Now this pi 2px and pi 2py are at the same energy level, so we can write equal to. So even if you write y before or x before or y, does not matter. Okay, so Drupad, how many electrons are present in the bonding molecular orbital? 1, 2, 3, 4, 5, 6, 7, 8. There are 8 bonding molecular orbital electrons present. In how many are present in the anti-bonding? There are 4 present. So the Nb minus Na is equal to 8 minus 4. It's a positive value. Therefore, it will become stable. Okay. So bond order becomes what? 4 upon 2 is equal to 2. So 4 upon 2 gives us 2. So there is a double bond that is present between the two carbon atoms. What else? What else? What else? So it is diamagnetic in nature, Drupad. Is there even a single molecular orbital that has an unpaired electron present in it? No, it does not have even a single electron which is unpaired in any of the molecular orbitals. Therefore, it becomes diamagnetic. It is a double bonded molecule. It is diamagnetic in nature. Till now, any problems? Okay, it's easy, right? This is a very easy topic. So, it is diamagnetic in nature. It is important to note that in C2, both the pi bonds are present because of the presence of 4 electrons in the 2 pi molecular orbital. Generally, in other molecules containing double bond, one is a sigma bond and the other is a pi bond. Okay, but here both the electrons are present in the pi molecular orbital. Now, let us actually look at the case of oxygen, the one that we have been waiting for a long time. Now, again, I'm going to draw. This time, I'm going to draw a little bit better because it's oxygen. Okay, so you have, this is your sigma 1s2, sigma star 1s2, sigma 1s2, sigma star 1s2. Then you have sigma 2, 2s. Sorry, you should not write or you should only write sigma 1s and sigma star 1s. You are not supposed to write this 2 here. Okay, sigma 2s, you have the sigma star 2s. Then you have the sigma 2pz because it's oxygen, so sigma 2pz. Then you have the pi 2px, pi 2py. Then you have the pi star 2px, the pi star 2px, pi star 2py, and then you have your sigma 2pz. Okay, now what is the electronic configuration of oxygen? 1s2, 2s2, 2p4. No, 2p6, right? No, not 2p6, 2p4, right? 4, 5, 6, 7, 8. Yeah, 2p4. So this is 1s, 1s. This is 2s, 2s. This is 2px, 2py, 2pz. This is again 2px, 2py, 2pz. So 2 electrons and 4 electrons. Okay, 2 electrons here, 2 electrons here, 2 electrons here, 2 electrons here. Then you have 1, 2, 3 and 4. 1, 2, 3 and 4 electrons here. Now we have to arrange them. These 4 electrons go here, these 4 electrons go here. Okay, now we have to distribute these 8 electrons. Now 1, 2, 3, 4, 5, 6, 7, 8. Okay, now this is how the arrangement goes. So first things first, electronic configuration. What is it going to be? Sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. Then you have sigma 2pz2. Then you have pi 2px, 2px2, pi 2py2, and then pi star 2px2, pi star 2py2. Okay, sorry, not 2px2 but 2px1. So this is for 1 mark, 1 mark. Okay, understood? So you have written the electronic configuration here. Next, stability. Nb is equal to how many bonding molecular electrons are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. Na is how much? 1, 2, 3, 4, sorry, 3, 4, 5, and 6. So, Nb minus Na is equal to how much? 4. Then, this is stable. What about bond order? 1 by 2 Nb minus Na is equal to 4 upon 2 is equal to 2. Therefore, 2 means double bond. 2 means a double bond exists between the two oxygen molecules. What else can we say? Now, since there are unpaired electrons present in the pi star 2px and pi star 2py, O2 O2 molecule is dimagnetic. Sorry, not dimagnetic, paramagnetic. Paramagnetic in nature. So it means that if you place it in a magnetic field, it will get slightly magnetized and get stuck to the magnet. Okay. Did you understand this whole concept, Dripat? How to draw the molecular orbital? Okay. Now I'm going to show you a video. Just hold on a second. Nothing happens, right? So liquid nitrogen is basically frozen nitrogen. When you freeze nitrogen below its melting, below its boiling point, it becomes a liquid. Okay, so nitrogen is not paramagnetic in nature. Nitrogen is dimagnetic. So due to this, what happens? The nitrogen will not get stuck to the poles of the magnet. But let's take the example of oxygen. See, can you see? See, Drupad, the yeah, right? So this is the reason, because the liquid oxygen molecule in its molecular orbitals it contains unpaired electrons. These unpaired electrons can be influenced by an external magnetic field. Okay, because they are getting influenced by this external magnetic field, so they are aligning themselves along the direction of the magnetic field. Thus, they are getting stuck between the poles of a magnet. It's beautiful, right? Okay. So, so the O2 molecule, because of the unpaired electrons present in the pi star 2px and the pi star 2py molecular orbital, they get stuck between them, and then due to this, they are being influenced by the magnetic field. Is this clear, Drupat? Okay, you got a visual understanding of how the paramagnetism and dimagnetism behaves, right? So, if you look at the case of nitrogen, how many electrons would have nitrogen had? It would have only had basically uh, uh, 1s2, 2s2, 2p, 2p3, right? 1s2, 2s2, 2p3, that is nitrogen, right? Oh, why can't I remember? 1s2, 2s2, 2p3, yeah, 7 electrons. Okay, so it would have only had 7 electrons, and in the case of nitrogen, there wouldn't be any this electron and this electron. So it would have become diamagnetic in nature. Thus, it does not get influenced by the electrons that are by the magnetic field from the external environment. But in the case of oxygen, because there is unpaired electrons present, what happens? It gets influenced by the magnetic field. Am I clear? But okay, let's move on. Let's move on actually. Okay. So the oxygen molecule, we have already done this. Bond order is 2. So the bond order 2 indicates that the atoms are held by a double bond. Further, two unpaired electrons are present in the pi star 2px and pi star 2py molecular orbitals. So O2 is a paramagnetic in nature. Similarly, the electronic configuration of some of the homonuclear and heteronuclear electronic molecules and their ions can be found out, which is given in this table. Okay, so H2, H2 plus, H2 minus, then you have helium 2. Helium 2 does not exist. Why? Because the number of electrons present in the bonding molecular orbital and that present in the anti-bonding molecular orbital are the same. Therefore, bond order is 0. Therefore, it does not exist. So, they could ask you a question in the MCQs and ask you which of the following atoms or molecules, which of the following molecules can exist in nature. Okay, so whenever the bond order becomes 0 or negative, you say that this type of molecule will not exist. Okay, clear, Drupad? Okay, now in the next class, no, the class is not over yet though. In the next class, I also want to study this a little bit because I don't want to give you incomplete information. The heteronuclear molecular orbital, even I have a little bit doubt in drawing them, but for the homonuclear ones, it is pretty easy. Now, Ne2, will it exist? It won't exist because the bond order is again 0. So, neon is what? Neon is a inert gas, right? Therefore, neon 2 molecule will not exist. Similarly, your Ar2 molecule will not exist. Similarly, your Be2 molecule will not exist. Okay, these are the molecules that do not exist. He2 molecule will not exist. Okay, because again the bond order is 0. So, if you just remember these three, it is more than enough. Beryllium, Be2, He2, and uh, Ne2, neon 2. Okay, so these type of molecules do not exist in nature. So we are almost at the end of this chapter. Okay, the final topic that we have to learn is the hydrogen bonding. Okay, it is a very special type of bond that has allowed basically water to exist in a liquid state. Okay, this is a very interesting type of bond. So listen to me very carefully. Now, what is a hydrogen bond? The attractive force which binds the hydrogen atom of one molecule with the highly electronegative atom, that is fluorine, oxygen, or neon of the same or another molecule, is called a hydrogen bond. Now, this exists like this, Drupad. See, you have an H2O molecule. Can you tell me the shape of the H2O molecule, Drupad? What is the shape called? Bend shape, exactly. Now, we all know that oxygen is what? An electronegative atom, whereas hydrogen is what? An electropositive atom. Okay, therefore, the lone pair of electrons will stay closer to the oxygen atom compared to that of hydrogen, thus resulting in a polarity. Polarity between the hydrogen and the oxygen. Now, this hydrogen atom has what? This hydrogen atom is now very near to another water molecules, oxygen. Okay, now this oxygen atom and this hydrogen atom, they both have opposite polarities. The magnitude may be the same, but they have opposite polarities, and opposite polarities usually do what? They attract each other. Am I right? So the hydrogen atom of one molecule is attracting an electronegative element of another molecule, thus actually forming a bond here. And this bond is called the hydrogen bond. This is the first bond that you are going to study. Oh, I think the second one, because you have already discussed van der Waals forces, van der Waals bond. So the hydrogen bond is an intermolecular bond. There are two types of bond, Tripat. One is called the intramolecular bond, MOLECULAR, and then the other is the intermolecular bond. Now, intramolecular bonds are the bonds that are present inside the molecules itself. That is the bond between this oxygen and this hydrogen. Okay, or this oxygen and this hydrogen. These are the intramolecular bonds. But the bond formed between two molecules is called an intermolecular bond. Okay, so what is happening here? The attractive force which binds the hydrogen atom of one molecule with the highly electronegative atom, fluorine, oxygen, and neon, of the same or another molecule is called a hydrogen bonding. Now, in hydrogen bonding, the presence of hydrogen has to be of the utmost priority. Okay, these type of bonds are formed between any two electropositive and electronegative atoms. Okay, they form. Okay, this is not something that is very unique to hydrogen, but because hydrogen in all the molecules has a polarity, a positive polarity, it produces a lot of molecules which have hydrogen bonding in them. That is the reason why we study hydrogen separately. That is the reason why we study carbon separately, because carbon has various properties which gives us various different molecules. The organic molecules are called carbon based molecules, right? So in the case of hydrogen fluorine fluoride molecule, the hydrogen bond exists between the hydrogen atom of one molecule and the fluorine atom of another molecule. Okay, now similarly, there is a hydrogen bond that is being formed between the hydrogen atom of this molecule and the oxygen atom of another molecule. Okay, here hydrogen bond behaves like a bridge between two atoms that hold one atom by a covalent bond and the other by a hydrogen bond. So it is forming a bridge so that it can keep these two molecules close to each other. Now, what is the cause of formation of the hydrogen bond? It is exactly as I said before. If hydrogen is bonded to a highly electronegative element, say X, like in the case of nitrogen or fluorine or neon, okay, sorry, nitrogen, fluorine, or oxygen, they are electronegative elements, right? The shared pair of electrons moves far away from the hydrogen atom because they are more selfish. They would rather keep the bonded electrons towards with them. Consequently, the hydrogen atom becomes highly electropositive with respect to the other atom X. Since there is a displacement of electrons towards X, the hydrogen acquires a partial positive charge while the X gains a partial negative charge. Like here, hydrogen has acquired a partial positive charge, whereas oxygen has acquired a partial negative charge. Okay, now, it results in the formation of a polar molecule with electrostatic force of attraction as shown below. So, there is an electrostatic force of attraction between the two atoms of two different molecules because of the presence of an electronegative element next to a hydrogen atom. Okay, now it results in the formation of a polar molecule with electrostatic force of attraction as shown in figure. So this is hydrogen X, H, X, H, X. The magnitude of hydrogen bonding. The magnitude of hydrogen bonding also depends on the physical state of the compound. This is why I told you water exists in liquid state because of the presence of so many hydrogen bonds in it. The molecules are kept very close to each other. This is also the result of life. Okay, on earth life depends on water. Okay, and water to liquid water, basically it depends on liquid water. Liquid water exists in such a state because of the tremendous amount of hydrogen bonds that are being formed between the two hydrogen and the electronegative oxygen. Okay, The magnitude of hydrogen bond also depends on the physical state of the compound. In the case of solids, it is maximum, and for gases, it is minimum. Thus, the hydrogen bonds have great influence on the structure and physical properties of the compounds. They have a huge influence on such compounds. Now, types of hydrogen bonds. You can have a hydrogen bond inside the molecule itself. That is known as intramolecular hydrogen bond. Or one atom of hydrogen could influence another electronegative element of another molecule, which gives us the intermolecular hydrogen bond. Okay, now what is the difference between inter and intra? I have already explained. So let's look at an example. Such bonds exist between two different molecules of the same or different compound. For example, hydrogen bond in the case of HF molecule, alcohol or water molecule. It results in the association of two molecules and hence results in the increased melting point, boiling point and solubility. Now, if there are more bonds existing between the different molecules in a state, what happens? It becomes more and more difficult to individually remove them. So to make them into a gas or to make them into a liquid, you have to provide more energy. Okay, so the increased amount of hydrogen bond between the two molecules will result in more solubility. Okay, more solubility means what? So basically, if a molecule can produce a large number of hydrogen bonds, like in the case of alcohols, if you dissolve them in water, they will quickly, the alcohol molecules will quickly form hydrogen bonds with the H2O molecules in water and result in quick solubility. Okay, so that is the reason why the alcohol is actually soluble in water. Okay, similarly, the melting and boiling point also increases. Now, in the absence of hydrogen bonding, you did not require that much amount of energy to actually boil a molecule, okay, to convert the state of a molecule. But now that there are more bonds present between two different molecules, you have to provide more energy to break these bonds. Therefore, the melting point and the boiling point also increases. The more bonds that can be formed, the more hydrogen bonds that can be formed between two different molecules, the more solubility you have, the more melting and boiling point you have. Okay, did you understand this? Now, this is p-nitrophenol, para-nitrophenol. You're going to understand more about this in the organic chapter. Okay, the nitro group, the OH group, and all of that. Just remember, whenever you have phenol is what? Phenol is a benzene ring with an OH molecule, and nitro is what? You have an N here, a double bond O here, and an O. So what is happening here? It is forming an intermolecular bond between the two molecules of phenol, thus resulting in hydrogen bond. Okay, now just one second, Drupad. So next, what we have is the intramolecular hydrogen bonding. Now, the hydrogen bonding that is present inside the molecule is called an intramolecular hydrogen bond. Such bonds exist when a hydrogen atom is present the hydrogen atom is present in between two highly electronegative atoms present within the same molecule. The O-nitrophenol, the hydrogen is in between the two oxygen atoms. Okay, so this is one oxygen here, one oxygen here. So instead of forming a hydrogen bond with a molecule next to it, it is forming a bond with it itself. Therefore, this bonding prevents the association of molecules, making the molecule more chelating in comparison to molecules where the intermolecular hydrogen bonding occurs. Hence, it decreases the melting point, boiling point, and solubility. So, Drupad, both these ortho and para nitrophenols they are isomers. They are chelating molecules. Okay. Now, chelating is a term that you're going to learn more about in organic chemistry. Okay, chelating molecules. Now, what happens here? The para-nitrophenol is able to form hydrogen bonds with the nearby molecule. Whereas in orthonitrophenol, this hydrogen atom is forming a bond with the oxygen atom of its own molecule. Okay, so in the previous case, what was happening? A whole network was being formed due to the hydrogen bond. But in the orthonitrophenol, the hydrogen bond is not forming a network. It is not forming a network. Basically, all these molecules could be in isolation, right? They're not forming a hydrogen bond with each other. So basically, everything will be lower. The solubility will be lower. The melting and boiling point will be lower. Okay, so this is how hydrogen bonds, the presence of hydrogen bond and how they are present in a molecule greatly affects the physical properties of the molecules. Okay, so hence the decrease in the melting point, boiling point, and solubility. For example, orthonitrophenol has a lower melting point and boiling point as compared to the para-nitrophenol. The reason for it is what? The lack of intermolecular hydrogen bonds in the orthonitrophenol. Understood? So, if you form a network, your boiling point, melting point, solubility all increases. But if you do not form a network and do not form a network, then your melting point, boiling point, and everything decreases. Okay, did you understand the hydrogen bonding concept? Okay, so with this we have finished. With this, we are there any doubts in this hydrogen bonding section? Are you sure? No doubts, right? Did you understand the concept of MOT very well? In the exam, you have to state all of these. Okay, you have to write a small theory. Okay, and then you have to draw the structure. Okay, the structure should involve these bonds. Okay, I forgot to draw them, but you have to draw them. Okay, now it should be neat and clean. It should be made with pencil. Okay, pencil and scale and all of that other stuff. Okay, you need to write the electronic configuration of the atomic orbitals first. Then you have to write the electronic configuration of the molecule. Then you have to write the stability, the bond order, the nature of the bond, and the magnetic properties. And that's the end of molecular orbitals and hydrogen bonds. We have officially finished this chapter. Okay, we have officially finished this chapter. Now, after a couple of classes, we will actually go through the questions once more to understand this chapter much more deeply. Okay, so I'm ending this video here. Okay, so students, if you liked the video, please do like, share, and subscribe. And I will bring you more videos like this with better explanation in the future classes. Thank you so much and have a nice day.